think we started discussing the postulates of quantum mechanics, and we had started actually discussing the postulate 2. So just let me recall what is postulate 2. Now postulate 2 says that for every observable, there is an operator in quantum mechanics, and this operator is special. Why special? Because this operator has to be linear, it has to be Hermitian at the same time. So in the last class I mentioned that, for example, if I go back to classical mechanics, then in classical mechanics, if I am considering motion in one dimension, for simplicity you can consider a motion in one dimension. Actually, if you take a particle, it has motion in 3D, but for simplicity, if I assume that it has a motion in one dimension, then the position is given by x, and the momentum or the linear momentum is called p or px. Okay, and the kinetic energy is p square by twice m. And if the particle is subjected to some potential energy, then it is usually denoted by a symbol V, capital V, which is a function of x, position of the particle. Is this clear up to this? Okay, if you have any question, just interrupt. But I think it's going fine. And we'll discuss about this operator. So essentially in quantum mechanics, this thing will be replaced by corresponding operators. For example, position, it is multiplication by the position coordinate x. For momentum, it is actually this is minus I h cross del x. And this is the momentum operator in quantum mechanics. And this operator is linear, and we will later show that this is Hermitian. Why it is linear? I just come back. Remember that. Can you see this? Can you see my cursor? Or maybe I'll just use another color. So, for example, operator is what? If my operator is A with a cap, it operates on a function, it gives you another function G. It operates on the function f, it gives you another function G. Example is a differential with respect to x. It operates on the function f of x, it gives you g of x. G of x is nothing but in this case, it's the first derivative of f of x with respect to x. You know this notation, f prime x? How many of you know?
Yes, sir. Yes, sir.
I can hear only one voice.
Yes, sir.
Yes,
Yeah,
sir.
yeah, okay. So this is a notation anyway. So what about this operation, this taking differentiation? Now, if I take two functions of x, f1 and f2, and I operate make an operation just by applying operator a on the sum of these two functions, and if it is so that it is equal to a operating on f1, a operating on first function plus a operating on second function, then I call that this operator is linear. Okay, if this property is satisfied. If this property is satisfied, then this operator A is called linear operator. Okay. Now it seems that this is obvious, but do you think this is obvious? This is not obvious. This is obvious for d of d by dx. So essentially, if I take a differential of these two functions x square, if I take two functions, if your f1 is x square and if your f2 is exponential of minus 2x, then taking differentiation of the sum of these two functions is equal to taking the differentiation of the first function plus taking the differentiation of the second function. I don't want to do it. This is obvious, isn't it? Do you think I should do it, or you can follow? Can you follow this? So you guys are following what I am saying? Yeah. So the idea is very simple, because if I take ddx of x square, if I take ddx of x square, so what I'm going to get? If I take ddx of x square, so let me write it down here.
2x.
Yeah. So I'm calling it g1 and g2. G1 is this one. So essentially G1 is what you get by operating A on F1. So it will be 2x, and in this case it is going to be what? Tell me.
Minus 2 e raised to the power minus 2x.
Okay. And if I take a sum of these two functions, which is essentially, I write it down here, x square plus exponential of minus 2x, and I operate on this, and you see that this is going to be nothing but 2x minus 2. Essentially, this operation is linear operation. So the operator is linear. This is obvious, no? But if I take an operation which is just taking a square of that function, in that case, this linearity of this operator is no longer there. So operator is no longer linear, isn't it? Are you following me?
Yes.
Right?
Yes, sir.
So let me write down
Yes,
here.
Yes.
So my operator itself is taking the square. So if I take a square of the sum of these two functions, which is this is obviously not equal to taking the square of the first function plus taking the square of the second function, isn't it?
Yes.
Huh? So it basically tells you that, okay, this operation is non-linear. So this not a linear operator. And we will not encounter such an operator in quantum mechanics. Okay, so you will encounter operators which are, for example, linear operators. So ddx, you already have told you that px is minus ih cross ddx. So this is obvious. Ih cross is just a number with a minus sign. Okay, so this is obvious that your linear operator in quantum mechanics, your momentum operator in quantum mechanics is linear. Huh? Are you fine? So now let us, now let us discuss this operator in little more detail. So I told you that in quantum mechanics, your momentum operator, which is in one dimension, I am writing, better to write with a hat. This is minus ih cross del x. Actually, you can write ddx also. You don't need to write partial in this case. But anyway, let it be like this. Okay. This is fine. This is fine. So if this is so, what is kinetic energy? You know from classical mechanics, kinetic energy what?
P square by 2m.
So px square, we are considering in one dimension. So px square by 2m. So what will be the operator in quantum mechanics?
Minus h square by 2.
So basically you have to replace px with px hat. So in kinetic energy operator, is going to be, what I'm going to 1 by 2m is a constant, I take it out. And then I'll have minus ih cross del x. And also this is one px, then you have to multiply this with another px, isn't it? These are again constants. If I take them out, what I'm going to get? I square is minus 1. I square is minus 1. Okay. And this minus minus will give you plus. So essentially what I'm going to get minus h cross h square by twice m, and I have this. This is one way. Why it is so? Because this is like operating del del x, and then I have this. This is essentially you're taking second derivative, isn't it? What you have is this. What you have is this. Okay, this is convinced because ddx is a linear operator, and operating ddx twice is equivalent of taking second derivative, isn't it? So taking the first derivative twice is equivalent of taking second derivative. So that's why the kinetic energy operator in quantum mechanics is this. Are you convinced? If you have any problem, tell me. Okay. Just tell me. For position, you have this x hat, which is multiplication. And what about this? I also have dx. You can put a hat there. This is the operator for potential energy. This is kept like this. So if I write down the Hamiltonian, which is the total energy of the system in classical mechanics, no? Are you following? Just tell me. Anyone who is not following? Yes, yes. Sometimes you tell me yes sir, so that I understand that you are there. So Hamiltonian in classical mechanics is your total energy. Which is your kinetic energy plus potential energy. And now when I go to quantum mechanics, what I have here, if I go to quantum mechanics, what I have here is an Hamiltonian operator, isn't it?
Yes, sir.
And what is this operator? Usually we note it with H and hat, the Hamiltonian operator. Actually, unfortunately, in chemistry, we don't learn much of classical mechanics in most of the chemistry curriculum, and we learn about Hamiltonians and others when you start learning quantum mechanics. But essentially, it comes from classical mechanics, but you have corresponding operator in quantum mechanics, which is your Hamiltonian operator. And this has to be your kinetic energy operator plus potential energy operator. So it has to be like H cross squared by twice m. So I can write dd. So this one, yeah. Is this clear?
Yes, sir.
Is this clear?
Yes. Yes, sir.
Okay. Now what about in 3D? This is in 1D I'm doing. No? So let us do something in 3D at least. So just in 3 dimension, what do you get? What is the momentum operator? Any idea what is the momentum operator? It will have 3 components, isn't it? It will have px, py, and
Easy.
pz or pz. Okay. And the px is obvious. It is going to be minus ih cross del del x. What about py?
Minus IH squared del by del y.
minus I.
And this guy is obvious, no? Okay. So similarly, you'll have a momentum square divided by twice m your kinetic energy, and this is going to be what? Px square by twice m plus py square by twice m plus pz square by twice m. Okay, are you convinced? So the corresponding operator is going to be what? Kinetic energy in 3D. Can anyone tell me what is going to be? You already know in 2D. So essentially what you have is h cross square by twice m, that constant. Yeah,
Minus
that is the constant. You take it out, and essentially you have
then
By del.
del.
Plus.
plus, it is inside the bracket. Huh?
Yes, sir.
Sorry for this. I have kind of learned little bit writing with this tablet, writing it better today for some reason. Anyway. So this is your operator, and usually we are very lazy. We don't write it like this. What we write? We write something like this: h cross square by twice m. Okay, minus is there, huh? Into what?
Hermitian
Laplacian.
square.
Laplacian square. This is notation.
Square.
Huh? Okay. So in now you know what is in 3D. So this page is very important because this gives you a prescription to build operator in quantum mechanics, isn't it? Okay, this gives you prescription to build operator in quantum mechanics. This is fine. Any question so far? Ask me. Okay, now I'll go to now. I told you that in quantum mechanics you have linear Hermitian operator. I have explained what is an operator. I have explained what is a linear operator, but what is Hermitian operator? Now consider you have an operator A. Okay. Consider you have an operator A operating on a wave function psi. Okay. It is clear, just operator A operating on a wave function psi. I've told you that it can give you anything, for example. And then what you do, you multiply this thing from left with another function phi. Sorry. Multiply this from left side to another function phi and take a complex conjugate of that, and you multiply with the volume element d tau. In 3D, if you have one particle, it is dx dy dz. In 1D, it is only dx. And if you integrate this, you get what you are going to get. Tell me, any idea? Because you have an operator operating on a function, and then you multiply the whole thing with another function phi star, which is the complex conjugate of phi. So whenever I say, if I take a function phi and put a star, it basically means complex conjugate of phi. Is this clear? Hey, Vijaya, say yes.
Yes.
Okay, there was it. Good. Anyway, I don't know because I cannot see you guys, so I am just guessing whether you guys are following. Okay, now the idea is very simple because if you operate a on psi, multiply with another function phi star, integrate, what are you going to get? You don't need to know quantum mechanics. Tell me. Integration will have some limits, no? So after you do this, all this thing, what I'm going to get, you're going to get some number. Are you convinced that you're going to get some number?
Yes, sir. Fine.
So this will give you some number. Now you can do another operation. You can do another operation. What is that operation? You can now take a and operate this a on say this function phi. Instead of operating on psi, you operate on phi, and then you multiply this with psi star. Okay, you multiply this with psi star, again multiplied with the volume element d tau, and then you integrate over whole space. What are you going to get? You're going to get another number because this is an integral, definite integral. Are you convinced that this is a number?
Yes, sir.
The whole thing is a number.
Yes, sir.
Now, if the case is such that this thing, and if you take again the complex conjugate of that number, what you get? You understand? You do this operation and take a complex conjugate of that number, you will get another number. And if these two are equal, then the operator A is Hermitian, and this is the definition. Okay? Any question? So this is the mathematical definition of Hermitian operator.
Hello, sir.
Yes, yes.
Sir. Sir, is there any physical significance of this Hermicity thing? Because like we have always studied ki the operator should be Hermitian and then equate and all this, but what is the physical meaning behind it? Like why it has to be Hermitian?
Okay, good question. Now, as a consequence of that, which will prove later, this means that Hermitian A, which is an Hermitian operator, okay? Has real eigenvalues, and that is, I think, very important. And that is very obvious and very important. I'm going to talk about eigenvalue in few minutes, but it tells you that Hermitian operators are such that it has real eigenvalues. Now, what is eigenvalue? I'm going to talk about. We will discuss about Hermitian operator more in detail when you introduce what is known as linear vector space. We'll discuss little bit and we'll talk about Bryan-Kate notation. Okay, so then we'll come back and do Hermitian operator. And there are other properties of Hermitian operator. You'll see that if you have Hermitian operators, then the eigenfunctions of Hermitian operator, they form a normal set. We'll discuss all these things. Okay, I'm not going to write it down here. So, but what is important here that I'm going to discuss what is known as eigenvalues. Very important, huh? So, what is eigenvalue? Huh? Let us write it down.
Hello, sir. This is Raman. Can I ask something?
Yes, I'll ask.
Yeah, is Hermitian operator restrict to real eigenvalue?
Yes, Ramanand. Yes.
Yes, sir.
So, Hermitian operator means it ensures that it has only real eigenvalues. And that is why it is so important in quantum mechanics.
Okay.
Now, let me discuss eigenvalues and eigenfunctions in next few minutes. So the idea is as follows. For example, if you have an operator A, operating on a wave function or any function, for example, and it gives you the same function back multiplied with a number, where a is a number. Now, follow very carefully my statement. Please follow. This number can be real or imaginary. If this mathematical structure is maintained, then psi is called the eigenfunction of the operator A. With eigenvalue small a, which is a number. It could be real or imaginary. This is very important. Up to this we are doing math. Now we will do quantum mechanics. But in quantum mechanics, QM means quantum mechanics, A is Hermitian. And this ensures small a is real. It basically means if I take A star, small a star, which is equal to A. So you are getting my statement. In mathematics, if this structure is maintained, the one I showed you here, this is the structure. That is an operator operating on a function gives you the same function back multiplied with a number. This number could be real or imaginary. Then the function psi is called the eigenfunction of the operator A. And that number small a is called the eigenvalue. And this equation is called eigenvalue equation. Okay, is this clear? Any comments so far? Any comment? Tell me.
Hello.
Yes, who is this?
Yeah, I'm Somesh.
Tell your name. Okay, Shomesh, yeah, tell me.
Sir, I have a question regarding operator.
Yes.
So, what differences it made in measurement while doing it in position domain or momentum domain?
See, you're deviating. I'm not going to answer this question because you know many things and you're asking that question. So please ask question. So far, what we have taught. I have not talked about measurement. Have I talked about measurement? I will talk about it later. Okay, and then I'll get back to you. So if you have question up to which you have covered, ask me that question. Okay, I'll answer your question later.
Hello,
okay,
sir.
Now
Harsha here.
Yes.
Sir, if the operator does not follow the hermiticity, like Hermitian operator, then
Yes.
then the eigenvalue of those function will be imaginary.
Yes, like if there's no Hermitian, there is no guarantee that this will be real. And if they're real and linear, it basically means this is an Hermitian operator. So in
So, sir,
quantum
how
mechanics,
is
we deal only with Hermitian operators. So don't think about anything which is non-Hermitian. In quantum mechanics, we deal with linear and Hermitian operators. We don't have anything which is non-linear or non-Hermitian. Spatial quantum mechanics, you may have it when you build operators which are non-Hermitian, non-linear, but that is different. But in the structure of quantum mechanics, basic quantum mechanics, or essentially how the theory is, all the operators are Hermitian and linear.
Sir, in what case the eigenvalue can be imaginary then?
If you have an operator which is not Hermitian, then it is imaginary. So let me give you an example. But that example is not going to be from quantum mechanics, but from mathematics. So
Sir.
yes.
Sir, so as you told, the eigenvalue could be real or imaginary, right? So now,
Yes.
what that eigenvalue corresponds means it corresponds to one of the values that we will be getting for the operator if
We'll
we
talk
measure
about it.
it.
We'll talk about.
So what
We'll
does
talk
that
about it
imaginary
again.
value?
We'll talk about it. We'll talk about it.
Okay, sir.
So
Okay,
there
sir.
is a
Okay, sure.
world beyond quantum mechanics. There's something called mathematics. Okay.
Yeah, sure, sir.
So let me explain what So for example, if I have an operator, let's say DDX, this is my operator. Okay, and I operate this on a function like ix, exponential of ix. What is the answer?
Iota e raised to the power iota x.
Okay, so but this has the same structure as this operator A operating on a function psi or phi, whatever you want to call it, gives you something like this. Okay, here in this case your psi is exponential of ix, and your operator is ddx, and your small a is what? I. But what is I? I is
Imaginary.
Root of -1.
imaginary. So now you have a eigenvalue equation. You have an eigenvalue equation, but with an imaginary eigenvalue, isn't it?
Okay,
You
sir.
understand? So this is an operator. In this case, ddx is an operator which is linear, definitely linear. Okay, but if I consider this function, it is exponential of ix. Okay, and on this, if I operate ddx, I don't get a real eigenvalue. So ddx is not Hermitian. If you consider this function, it is not Hermitian. Is this clear?
Okay, sir. Yes,
Actually,
sir.
this will be clearer when you deal with bracket notation. And of course, many operators do not follow eigenvalue equation. For example, if I take a square root of say x square, what is the answer?
X.
X.
Plus minus 6.
Plus minus x.
Yeah,
Plus minus
right. And then
Plus
I
minus.
stop. Okay. So, but this is not an eigenvalue equation, isn't it? So this is not an eigenvalue equation. Of course, this operator is nonlinear. So my point is, you can even have a linear operator which is not Hermitian. Okay, is this clear? So up to this, so I have done up to postulates, what is known as postulate 2, and now I'm going back. I'm now going to discuss postulate 3, which will answer many of your questions, and I'll try to finish today all the postulates. Recalling, very bad handwriting, sorry. Postulate 1, postulate 2, and postulate 3, which we have not done. So 1 and 2 will come back later. But what is postulate 3? Can you see what is written there?
Yes, sir.
So postulate 3 tells you that measurement of an observable would give one of the eigenvalues of the corresponding operator. So I have already introduced the idea of eigenvalue, and the postulate 3 tells you that there's something called measurement of an observable, and that would give one of the eigenvalues of the corresponding operator. Okay.
Sir,
So
what is the significance of knowing eigenvalue?
Yeah, we'll come. So just wait. Okay. So let us illustrate this. Because if I don't illustrate this, I will not be able to follow. So how do I illustrate this? With an example. So let us consider that you have a rigid wall. Actually, it's a metal, and somehow people have done experiments. You attach one hydrogen atom to this wall. This is like an hydrogen atom absorbed. This is called chemisorbed on this wall. And this wall, you can have a situation that this wall is like made of tungsten. Okay. And say for simplicity, I am interested in this is your x direction. And for simplicity, I am interested in displacement only in this x direction. So this is your wall, and this is where the ball, essentially the hydrogen atom, is attached as if with a spring, and it can go this kind of motion. It can do this kind of motion. Okay. Connected to the spring, and I'm interested in only in this direction. It can also go in this direction, or it can go towards me or away from me. It is z, this is y. I'm not interested. I'm only interested in the displacement in the x direction. Okay. Is it fine? Okay. So let me write down the Hamiltonian of the system. Any idea what could be the Hamiltonian? Hamiltonian operator. If I write it down, it is going to be h cross square by twice m in one dimension, no? Plus something, because we have and I assume that okay, the simplest possible model for this is such that the force acting on that particle, it is, because if you pull it this direction, it has a restoring force which will pull it back towards the metal surface. If I pull this, you can think of that you attach a ball with a spring to a wall and you pull it. And when you release it, it will go back to the wall. So there is a restoring force towards the wall. And this restoring force is actually proportional to the displacement. But since it is restoring force, it has a minus sign. And the displacement, I am calling it x. X is actually the displacement away from equilibrium position. Okay, this is displacement away from the equilibrium position. Is it clear? And there is a proportionality constant. I am calling it k, and k has a name. This is called force constant. And if you do the classical mechanics of this problem, you will see, since I know that your force is equal to minus of dv dx, negative derivative of the potential energy, isn't it? So this will give you my potential energy as what? Can anyone tell me?
Half K prime.
Yes,
Half K.
it is obvious, no? Because V is going
Yes.
to be minus
Integration
of f
K.
dx.
Yes, sir.
Say I from 0 to x, whatever. This is going to be plus a x 0 to x. Better to use x prime, dx prime. Okay, fine. Some other. So essentially, what I have is
K by 2x square.
this is here, and this is the model you use, and this is called simple harmonic oscillator. I think many of you would know, isn't it?
Yes.
So my potential energy is going to be half k x square. We will do the quantum mechanics of this problem later, but let us write down the result. Of simple harmonic oscillator. Which we'll do later, but you know the result. But here right now what I'm interested in the energy. And you'll see that if I find out the energy, you see this energy depends on something like a quantum number n, and the expression is given by n plus half. Sorry. And n is an integer, either 0, 1, 2, like this. So we have energies like E0 is half h nu, E1 is 3 by 2 h nu, E2 is 5 by 2 h nu. And then how many such values are possible? Any idea? How many such values are possible? Actually infinite, because there is no end. N goes from 0 to infinity, but it has to be integer. Okay. And these are called eigenvalues. Why eigenvalues? Because if you take this operator h, I'm sorry, if you take this operator h operating on the wave function psi, which will have a subscript n, this is the wave function, and you'll see that you'll get En times psi n, and the psi n is the eigen function of h, and these are the eigenvalues. So I now go back to postulate 3. If I design an experiment, and in that experiment I measure the energy of the harmonic oscillator, one-dimensional harmonic oscillator in this case. So each time I measure, I will get one value of energy, and that value has to be one of these eigenvalues. So I measure this time, I get it 3 by 2 h nu. Next time I measure, I get 5 by 2 h nu. So each time I measure, I get a different eigenvalue, or I can get the same, if possible. But I cannot get anything which is not the eigenvalue. So I just again go back to postulate 3. Postulate 3 says that measurement of an observable, yes, energy is an observable, would give one of the eigenvalues of the corresponding operator. So what I meant here, that each time I measure, I am going to get one of the eigenvalues. So the measurement, see here again I go back, see, measurement of an eigen. This is okay. So the measurement ensures you get only eigenvalues. Okay. And this is your third postulate of quantum mechanics. But this postulate will be clearer when I discuss something now, right now, which I should do, and then I'll take questions. Say uh, I do measurements and say uh, mm, mm, I do measurement many times and say n1 times I get eigenvalue which is a1 in general. Okay, so my a1 could be this half h nu. A2 could be this 3 by 2 h nu. This is my notation. Huh? A3 is 5 by 2 h like this. If you are doing only harmonic oscillator, but just think of a general scenario. You make measurements and you make measurement for n1 times. You get the value a1 for n1 times, n2 times value a2 like this, n47 whatever a47 like this. Okay, remember these n's are not quantum numbers. I use same notation, but these are not quantum numbers. These are number of measurements, number of times actually. Okay, these are not quantum numbers. Okay, and these are what? These are number of measurements. Okay, this is how it is. So how do you calculate then? So you can calculate some average, for example. If I calculate some average, how I'm going to calculate the average of A? Can anyone tell me? Maybe Pooja, can you tell me how do you calculate the average? Pooja.
Yes, sir. A1 plus A2 to up to AN divided by number of measurements,
Is it
total number of measurements.
not correct?
N1
It has
A1
to be
plus
like this
N2
because
A2 and so on divided by total
it
number
should
of
be
measurements.
N1 A1 A2 plus N3 A3 plus. The whole thing has to be divided by total number of measurements, which is N1 plus N2. It is like calculating the average value in chemistry lab. You do titration, no? So you do titration say 100 times. You never do 100 times, but say you do 100 times, and say 5 times you get some value, 7 times you get some other value, 8 times you get some other value, 20 times you get some other value. What is the average value? You have to take how many times you got value A1 multiplied with that number, plus how many times you got value A2 multiplied with that number, how many times, and you keep on adding and then divided by total number of measurements. Okay. So N1 plus N2 plus N3, that the whole thing will give you the total number of measurements. And this is called the average value, isn't it? Sorry. is the average value. Similarly, in quantum mechanics, there is one way of calculating average value. What do you do? In this case, in quantum mechanics, what you do, you take that operator A, operates on a wave function, the wave function psi, multiply the whole thing from left with another wave function psi, but the same wave function, but its complex conjugate psi star, and then you multiply it with the volume element, integrate over all space, and divide the whole thing by this psi plus psi, and this will give you something like the average value for that operator. Basically means the average value for the observable corresponding to that operator. And this has a name in quantum mechanics. This is also called average value, but it is better known as expectation value. Also known as average value. Same. Also known as mean value. But more frequently, you see that you use this, prefer this term, but it doesn't matter. So this is called the expectation value in quantum mechanics. So essentially, if you do the experiment many times and get many values, and then if you have the data, I showed you how to calculate the average. Similarly, in quantum mechanics, you have a prescription to calculate average, and this is how it is done. This is called the eigenvalue. Sorry, expectation value. I already mentioned what is known as eigenvalue, and now I'm introducing what is expectation value. So let me think of a special situation, and after that I'll take maybe I'll take questions. If you think of a special situation, okay, if psi is an eigen function of A, what will happen? Can anyone tell me? Now let me ask you the question. What will happen if psi is an eigen function of A?
It will give an eigenvalue and regenerate the psi.
Can you repeat?
Then we get a,
Yeah, please repeat.
we can get a constant value.
So let us try. So if it is an eigen function of A, it basically means that A operating on psi gives you something like small a, which is a number times psi, and I put this here. If I put this here, what I'm going to get? I'm going to get
A only.
Yeah, I'm just doing. I want to do d tau psi star. Now a psi is small a times psi. You have d tau psi star psi, and this is nothing but because you can take a outside, which is a number, and you will have d tau psi star psi, but you have the same thing in the denominator. So what I have here is A. Are you convinced? Basically, I'm saying that yeah. So basically, if your psi is an eigen function of A, then eigenvalue and the expectation value are same. The expectation value is equal to eigenvalue. Okay, and we will see it is not the case always. And one comment, there is something called measurement theory and quantum mechanics. It's a very active area of research. And we're not going to discuss much in this course. What do you exactly mean by measurement? Because when you measure, you get the eigenvalue. There is something called polar associated with measurement. I don't think we're going to discuss this in detail in this course, but we can have a special online class, not class, online session for people who are really interested. Okay, we can have it later. Rahul, you are there. Are you there?
Yeah, I'm. Yeah.
Yeah, so we can discuss that in detail later, maybe just for fun.
Yes,
We want
sure.
to have a session.
Sure, sometimes,
on,
sure,
yeah. So I am just giving you the framework of quantum mechanics, how it is done. So I'll just go to the next postulate because I want to finish all the postulates today, so that we can discuss things in the next class. The next postulate is called postulate 4, and it tells you that the state function, and you'll see that I'm calling it state function, but it's nothing but the wave function. See, in some book you'll see that they write like this, 2 words, wave function. In some books they write like this, together. I don't care how do you write, okay? Both are fine. So the state function obeys the time dependent Schrodinger equation, and you have written down the time dependent Schrodinger equation, which you should remember, which tells you IH cross partial derivative with respect to time on the total wave function on the state function psi gives you the Hamiltonian operator H operating on psi. So in general, this psi is a function of x, y, z, whatever the space coordinate and time. Function of space and time. Okay, and if I elaborate this, if I write it down, you know how to write it down now. This IH cross is going to be del psi del t. So I can call it r comma t. R means all the space coordinates. And when it operates on this, it gives you H psi. And you know what is H? H is minus H cross square by twice m into Laplacian square, and then you have potential energy in 3 dimensions. It will be a function of x, y, z. If you have one particle, so in general I can write is a function of r, which is, and the whole thing operates on this function psi, which is the function of r. And this is called time dependent Schrodinger equation, and actually if you tell me strictly speaking, this is the Schrodinger equation. This is called time dependent Schrodinger equation. In many books you'll see, Rahul, I think you'll agree that people, the eigenvalue equation, which you'll see that from here you can arrive at something like an eigenvalue equation, which tells you that the operator H operating on this side, this is different, this is a function of x only, function of space only. Space, and this will give you something like n e times psi, and this is called time independent Schrodinger equation, which I will do in the next class. And we'll see how you get it. Schrodinger equation. And more precisely, this is called eigenvalue equation. But you see that people loosely call this Schrodinger equation. So if I ask you write down the Schrodinger equation, usually you write down H equal to H psi. But the actual Schrodinger equation is the one which involves time derivative. The one I have here, the one I have written here. So now we have introduced all the postulates of quantum mechanics, the whole framework of quantum mechanics. from the next class onwards, what we are going to do, we are going to pick examples and illustrate this. But before that, what I'm going to do in the next class, which I'm not going to do today, I'm going to solve this equation. So in real, let me write down this potential energy G is also a function of time in general, which is r comma t. Okay, but we'll consider a case where it is not a function of time, it is only a function of space, and you'll see that if it's a situation like this, then it is possible to solve this equation using a technique and to get a set of solutions which will give you what is known as stationary state. And we'll talk about it in the next class. I think it is getting quite heavy. So I'll stop here. Now from here, I and Rahul, both of you can take questions. So please ask question if you have any. Anyone has a question? No question?
Hello, sir.
Yeah, Sachin Dev.
Sir, so in expectation value that we calculated,
Yes.
so if it is eigen function, then expectation value is equal to the real value. It is like that?
Not real value. Expectation value. You repeat your question again. Can you repeat your question?
Yeah. Sir, if it is eigen function, we got that the expectation value equal to a number.
What function? What
right?
function?
Eigen function.
What? Eigenfunction. See, the eigenfunction, if the operator is Hermitian, then the eigenvalues are real. So the expectation value is going to be real. And whenever you do any measurement, you measure something real. Your energy, momentum, these are real quantities, isn't it? Your energy, momentum, these are real quantities. So you end up with real things in quantum mechanics. You don't measure something which is imaginary. Okay. So your expectation value is always real in quantum mechanics. So as your eigenvalue. Yes. Maybe Rahul wants to say something.
No, this is perfectly fine. I just wanted to say that yes, if your state is a pure state, by pure state I mean that it's not a linear superposition state, then of course you have the possibility of getting only one eigenvalue. So naturally, very conceptually, you don't need to do mathematics at all. Very conceptually, if your state, your psi is just consists of say one function. So if you do the eigenvalue equation, naturally it has that particular eigenfunction, which is the which corresponding eigenvalue you get all the time upon your measurement.
Yes.
So, but if it's a go ahead.
I can illustrate that. I understand what you're saying here, but I did not want to do it right now. Maybe we'll do it later. But I can tell you thematically what is this. For example, what Rahul is saying that okay. You can consider a case. So I'm dealing with time independent things. So consider a case where your wave function, the psi, is something like linear combination of other functions. It is like C1, phi1 plus C2, phi2. It's a linear superposition.
Yes. So suppose you have two sets of eigenvalue equations. Suppose H1 of phi1 gives you A1 phi1. And H of phi2 gives you A2 phi2. So A1 and A2 are the corresponding eigenvalues.
So basically your psi is something like your sum over I, Ci, phi I, and the Hamiltonian of your system is H. But all these phi's are actually eigenfunctions of H. So basically if H operating on phi1, it gives you something like A1 times phi1.
And it is not necessarily Hamiltonian. You can have any function, any operator.
Yeah. I'm just giving you an example. Any operator, yes. So if I'm operating on phi2, it gives you A2. Right?
So now
you don't need A. You can 8. You can make it A. So essentially, if A operating on phi I gives you AI times phi I. Yes, Rahul.
So now suppose you are doing an infinite time of measurement. So what is the expectation value you get? So depending on the relative coefficient C1 or C2, you get A1 or A2. So remember, when you are doing these measurements, the system either gives you the energy of your corresponding eigenvalue corresponding to phi 1 or the energy corresponding to the eigenvalue of phi 2. So that means you will get either A1 or A2. But if you do this measurement infinite number of times, you get an average. And what is that average? The average is simply given by the expectation value. So if your C1 square plus C2 square, this is 1, that means your wave function is normalized, then you will simply have C1 squared times A1 and C2 squared times A2. That's your average value. Okay, C1 squared times A1, C2 squared times A2. That is your average value, assuming C1 squared plus C2 squared equals to 1. If this is clear, is this clear? Then we can proceed.
Yes, sir.
Okay. Now, if this is clear, Raushid, I can write it down also, actually, the expectation value.
Yeah, I'm going to do. But
yes.
This is important. What is important, this thing actually, because this is important, which you have not discussed so far. So let us write down the expectation value.
Yes.
Of A average, whatever. And it is going to be, this is psi star A psi. Okay. And what I'm going to do, I'm going to now replace psi with this. So what I'm going to do, let me do the math first. So the first one is like this operating on A, and then you have and then in the denominator also you have something like okay. Now these I are dummy variables, so let me do it the denominator first. Denominator is going to be what? These C's are like numbers. These are like numbers. Okay. These could be complex numbers also. So essentially what I'm going to get in the denominator is something like this. You have something like, what should I say? It is better to write something like sum over I comma j. Maybe it is something like, write it Cj star Ci, and then you have phi j star phi I. Okay, so in the denominator what you have is d tau, and I told you that phi j star phi I d tau is 0 if I is not equal to j, which essentially tells you that in general I have an integral like phi j star phi I, which is given by delta ij, delta ji, isn't it? This is a Kronecker delta actually. So this is 0 if I is not equal to j, otherwise if I equal to j, then this value is 1. So essentially only when I equal to j, the value will survive, isn't it? Other value will not survive. So essentially I will have something like sum over mod of Ci square, sorry for this, into phi I star, okay, let me do it, phi I star phi I Now what is this integral? Can anyone tell me? You know what is this integral? If I equal to j, and this integral equal to 1.
1.
So essentially in the denominator you have nothing but sum over I mod of ci square. Isn't it? Is this clear? Or if you don't like mod, just write ci star ci. I. So what about the numerator? So numerator, you see that these are numbers, no? Ci, these are coefficients, these are numbers. So in a numerator, what you have here is something like, so what you have here is something like, again I can club them together, something like Cj star Ci kind of thing, and then you have phi j star A phi I. Okay, is this clear? Rahul, this is what you want to show, no? Rahul, are you there?
Yes, I am.
Yeah. So now what is going to happen in the denominator? Now you know that, okay, that when A operates on phi I, I know it gives you AI, isn't it? It gives you AI. So what is going to happen here? Can anyone tell me? Finally, the answer. Because then you integrate this. We have essentially integration like this. And here again, only I equal to j term will survive. Isn't it? What is going to happen here? Can anyone tell me?
Sum over AI into mod ci square.
Yeah. AI into if I
Mod
something
ci
like this,
square.
isn't it? Yeah, sorry. Mod ci square or like this?
Ci star Ci.
Yeah, it's the same thing, right?
Yeah, same thing. I just writing more precise. Essentially, what you have is AI into mod ci square.
So you essentially get all the eigenvalues multiplied by the corresponding probability.
Okay. So basically, yeah, what Rahul is saying that, see, this is the eigenvalue. AI, you multiply it with its probability, which is ci star. Sorry, ci mod ci square. Ci star ci. That's the weightage, and you add them and divide the whole thing by ci star ci, which is again is nothing but here.
Okay, now tell me one thing. So suppose your ci squared, that gives you the probability, right? So if you have a normalized wave function, you know what is the normalized wave function? That it is normalized to unity. So what you are supposed to get, that if you sum over all the ci squared, by squared I mean the modular squared, what are you supposed to get? You are supposed to get 1, because it's a normalized wave function. So you can safely ignore the denominator if you have a normalized wave function. Now coming back to your question, you see that now suppose instead of having your psi as a linear superposition of different functions, if you have your psi just as phi 1, and you assume that your C1 is just 1. If this is what happens, you see that each time you do, you are just getting C1. You are just getting A1. All the time you do the measurement, you are always getting A1, because the other function do not exist and the corresponding coefficient is 1.
Yeah.
So that means in that case, your expectation value is same as your eigenvalue.
Yes. So essentially what he is saying, that a special case, I don't have space, but I can generate a space here. Sorry, because I don't want to go to another thing. So here I write down, say, a special case. Sometimes this pen gives you. what Rahul is saying. Okay. Some problem. Yeah. So special case is such. Some problem with my writing. You can see. So it is. Sometimes it gives you some trouble. Not always. Essentially, what Rahul is saying that okay, if I have only one phi, okay, and all the other phi's are 0. That is what you are saying, na Rahul? Rahul, are you there?
Yes.
Yeah. Yeah. So then actually you end up getting this the eigenvalue corresponding to phi. So you don't get anything other than that. So if only one phi exists, only phi 1, and all other phi's are 0, then your psi is actually something like, sorry, some problem with writing, but maybe Rahul you can explain with your words because some problem with
Yes.
writing here.
So I'm simply saying that suppose your second phi doesn't exist, so phi 2 doesn't exist. You have just psi equals to phi.
Yes.
And you know what you get? You have the eigenvalue equation, which is basically h phi 1 equals to a1 phi 1. Each time you measure it, you get a1. So now if you do say each time you get a1 and you do this averaging say upon measurement of 1000 times, each time you get a1. So eventually your average value is also a1. So this is what I am trying to say, that if you have a pure state, then your each measurement, it gives you the same eigenvalue and your expectation value is same as your eigenvalue.
So any question in next 5 minutes? It's a long class, I can understand. A long class, and we have already left.
So can you see the chat box?
Which one? Chat box. Yes. Sorry. Akash Ghosh.
Yes, sir.
Okay. So Rahul, the question is that whether you have to mention the function to say whether the operator is Hermitian or not.
No.
Because I think he asked that question because I choose that exponential of ix. Had I chosen exponential of say x, then that function ddx would appear Hermitian. That is
Yes, actually,
why the question is, isn't it?
Yes, actually, sir, you have just told that DDX is not an Hermitian operator when you choose a function that e to the power ix. So I just want to say that if the
right.
another function, so that time it may be it will be a Hermitian operator. So it is
yes. If I choose exponential of say x, no I, then it is linear as well as.
See, operator, whether operator is Hermitian or not, this is exclusively your operator property. It's exclusively your operator property. You don't have to, you can define your hermiticity of your operator irrespective of your function.
Yes. What Rahul is saying is correct, but the confusion is because we did not discuss Hermitian operator in detail. But Hermitian operator says that it is equal to its Hermitian conjugate.
But sir, you have just showed that the function that with respect to DDX is not Hermitian. But in another case, maybe.
Yeah, but you see that there is something called Hermitian conjugate of an operator. If I given A operator, then A dagger is called Hermitian conjugate. And if A equals to A dagger, then it is Hermitian operator. Okay, and that is independent of the choice of function you are operating on. Okay.
But if we consider that thinks that time, sir, it's become dependence. Hermitian operator
No,
become
that is appearing as if dependent, but that is not. That is only one subset. There is one subset of function to which, if you operate on that function, it will give you real eigenvalue, but it does not tell you that. So essentially, Hermitian operator is such that independent of the nature of the function, it always has real eigenvalue. Rahul, I think that is the statement, isn't it?
Yes. So, for example, if you have a say free particle, your what is your corresponding eigenfunction? Your corresponding eigenfunction is not the most general eigenfunction, is not e to the power kx. E to the power kx is a very special solution, which may not give you your real eigenvalue. You have to write it as e to the power ikx or e to the power minus ikx. Rather, e to the power plus ikx is plus e to the power minus ikx. This kind of so that you get so that you get a kind of a real eigenvalue.
What Akash is saying is obvious. It will appear to what I have said so far. It will appear that it depends on the functional form, but actually it's not the case, because it is one on subset, but actually Hermitian operator is such that all of its eigenvalues are real.
Yes, sir. From there, sir, the confusion is arises.
No,
I discuss many things in detail. So that's
yeah, we will discuss this one maybe. Yeah.
When you do linear algebra and you go to bracket notation, and there is something called vector space and so Hilbert space. So I think it will be clearer.
That means that the conclusion is the Hermitian operator is independence of function.
No, the conclusion is when you talk about operator, you don't think about function. So Hermitian nature, that property of that operator is independent of the choice of function. It is, because when you define that A is Hermitian means A dagger equals to A, which we have not discussed, which we will discuss later.
Okay.
So Rahul, I think that is how we should do. Like, if we don't do linear vector space, it's very difficult to everything.
So basically, if you just write it as A dagger equals to A, see that this definition of your operator, so A is any arbitrary linear operator. This definition of your Hermitian operator is irrespective or independent of your eigenvalue or the function it is going to operate on.
Okay, so I think we'll wrap up today. We had a long class. We can discuss things on WhatsApp, and hope I'm going to send this video as we did in the last class. Okay, so we'll just wrap it up now. Okay, so have a nice day and be safe and healthy. Okay, and we'll meet day after tomorrow. Okay, thank you.
Thank you.
Thank you. Yeah, thank you. Yeah.
Yes, sir.
Okay.
Hello, sir. Hello, sir.